And this paper is about dynamic binary choice panel data models with fixed effects. And I will explain to you what these are. So here's the talk. I'll give you some general introduction, and then I'll give you some basic results. The paper is still in progress, so we only have some preliminary stuff to show you. So here's some just an introduction about the terminology. A panel data set, the statisticians here might call it a longitudinal data set. You can call it a grouped data, but typically in the economics and sort of other social sciences, we prefer to call it a panel data set. And a panel data set is essentially a collection of time series for a whole bunch of individuals. And the reason why this data structure is useful in applications, because it allows you to it allows you to incorporate explanatory variables or a kind of explanatory variables that are actually unobserved. So in the fact that you have variation coming from 2 dimensions, individuals and time, allows you to incorporate in your models certain kind of unobserved regressors or unobserved explanatory variables. The kind of unobserved variables that you can actually control for in these variables are variables such as ability or productivity or cultural preferences, which are known only to the individuals. They are not known to the economist or to the analyst who's looking at the data. So these are variables. Your productivity, your ability, your cultural preferences are known only to you, not to me. And the other crucial assumption is that these preferences are time invariant. So my preferences are different than yours, but over a short period of time, they're essentially constant. So these time invariant attributes, these time invariant characteristics, which vary only at the individual level and cannot be seen by researchers analyzing the data, typically we call them fixed effects. So here, fixed does not mean that they are non-stochastic. These are regressors. These are explanatory variables. They are fixed. The fixed simply means they are fixed over time, but they're not fixed across individuals, and they are drawn from a particular distribution. There are other names for these fixed effects. You can call them unobserved individual specific effects. You can call them unobserved individual specific heterogeneity. There's a whole bunch of different names. Of course, you can have other time invariant variables in your models, variables such as ethnicity or gender or even completed years of schooling and stuff like that. But these time invariant variables are typically observed by the researchers analyzing the data. Okay, so, oops. It's not going back. Yeah. Below is below is back. Okay. I never use this thing. I know. Very good. Okay, but the forward is this one, yeah, the big one. So here's the notation. So we will index individuals with I, and there are n individuals, little n. You can call them strata. Statisticians, I think, like to call them strata. We will call them individuals. There are t time periods, cap t time periods, and each time period will be indexed by little t. Yit will be the outcome, whatever it is, of individual I at time t, and the x's will denote the explanatory variables in your model. Alpha I0 will be our symbol for the fixed effect. So this is an unobserved, time invariant random variable. The crucial assumption here is that the joint distribution of the fixed effects and the unobserved characteristic and the observed characteristics, the x's, is completely unknown. So we are not making any distributional assumption about the joint distribution of the observed and the unobserved characteristics. And in particular, the correlation between these objects is completely unrestricted. So for example, there are several examples of these kinds of sort of panel data models. You can have a linear model where sort of the variables and the parameters enter the model linearly. You can have a dynamic version of these linear models where you simply allow for intertemporal relationships by including, for example, one lag or two lags or k lags, whatever. And you can have nonlinear versions of these models. So for example, you can have a static nonlinear panel data model, which would be, for example, a Poisson model. You can have dynamic version of the Poisson model. And if the y's are Bernoulli random variables, you can have a binary choice model. So for example, you have a static binary choice model where y is 1 if the condition inside the parentheses is satisfied, and you can have a dynamic version of this binary choice model. And in these models, you cannot simply ignore the presence of the fixed effect, because if you simply ignore the fixed effect, then because the correlation, you cannot claim that the correlation between the x's and the fixed effects is 0. You basically end up with regressors that are endogenous and sort of, standard estimation methods break down. So really, these fixed effects, these unobserved explanatory variables have to be accounted for when you are handling these models. The kind of panel data models that we are interested in, at least I am interested in because I do microeconometrics, are what are called short. So typically, the idea of a short panel is, what is the justification behind the fixed effect being fixed over time? And the justification is, well, the time is small. So the length of the panel or the duration of the panel is short enough that you can justify that the productivity or the preferences, the unobserved preferences of the agents during the length of the panel are essentially time invariant. And so short here simply means that the number of observations, n, is much larger than the length of the panel, cap t. So typically, when the theory of statistical inference is developed for these models, it is developed in the setting that n gets large and t stays fixed. In this setting, it is well known how to handle linear models. And you don't have to make any distributional assumptions. You can use an instrumental variables approach. And this is sort of very, very standard, and there's a very large literature on this. Nonlinear models require basically a distributional assumption. Even then, even after you make a distributional assumption, these nonlinear models, you can handle only a few of these nonlinear models satisfactorily. So for example, you can, in the previous case, if the distribution of the model errors was logistic, so you have a binary choice logit model, a panel logit model, it turns out that you can estimate this relatively straightforwardly by conditioning on a sufficient statistic. But if you change the specification slightly, so if instead of logit you want to look at a panel probit model, then it turns out that there is no sufficient statistic. And so really the technique that works for panel logit simply doesn't work for panel probit. So our goal, and so this is now, we are working on this project. This is the third paper in this sort of project that we are doing, is really to develop a unified approach for estimating nonlinear panel data models in a parametric setting. So you make a distributional assumption about the likelihood, and the same technology or the same technique that works for logit will work for probit and sort of other specifications. And the theory that we develop is in a setting where both n and t get larger. But again, the restriction is that n will grow much faster than t, so the approximations are as if we are working with short panels. N is typically always much larger than t, even though both are getting large. So now I will show you our current project, which is basically looking at dynamic models. So here's a simple nonlinear dynamic model. It only has one lagged. It's an AR1 model, so it only has one lagged outcome as one of the explanatory variables. So y takes values 0 and 1, so it is a Bernoulli random variable. And you can think of y as indicating the state of the individual at a particular time. So the individual could be employed or unemployed. The individual could be sick or with corona or not sick. The individual could be a member of a union at a particular time or not, and so on and so forth. So this random variable tells you the state of this individual at a particular time, and the x's are sort of additional explanatory variables, and the alphas are fixed effects, these unobserved characteristics. For example, if you think of y as the state of employment, alpha could be, for example, your ability. Okay, so why are fixed effects important in these models? At least for economists, fixed effects are important. It is important to incorporate these unobserved random variables in your model because they allow you to distinguish between the sources of persistence in your outcomes. So for example, suppose there was no serial correlation in the x's, and there was no serial correlation in the u's, in the model errors. If gamma is equal to 0, so basically there is no lag-dependent regressor, so there is no serial correlation in the x's, there is no serial correlation in the u's, and gamma is 0, the y's are still persistent. There is still persistence in the y's. The y's are still dependent because of the presence of this common random variable across time. So the persistence in y is coming simply because of the presence of these fixed effects. To an economist, this is not a very interesting kind of dependence. It is essentially statistical dependence. To an economist, or maybe other social scientists, the kind of dependence or the kind of persistence that we are interested in comes because of when gamma is not equal to 0. So this is dependence or persistence that happens because of learning. This is the effect of, if you are unemployed in one period, well, that seriously affects your chances of being employed in the next period. This is the kind of persistence that economists typically are more interested in, and we like to call them, so gamma not equal to 0 refers to as true state dependence, and gamma equal to 0 is referred to as spurious state dependence. Anyway, so we make some standard assumption. So this is a nonlinear model. So we will assume that the u's conditional on the past x's are drawn from some CDF, some known CDF f, and f could be logit or probit or some other. It doesn't have to be logit and probit, and we are only conditioning on the past x's. So this is actually quite nice because conditioning on the past, only on the past regressors, allows current outcomes to essentially influence future regressors. And this is useful in applications where this kind of feedback happens. So for example, if this was a model of a female employment, then the decision of a female to work in a particular period T can influence the number of kids in future periods. So this kind of feedback between current outcomes and future regressors is actually very useful to allow for, and controlling only for the past helps us do that. So under these assumptions, you can compute the probability that y is equal to 1, and this is just this CDF evaluated at this index. And the objects of interest here are, you could estimate the common parameters, the beta and the gamma. So beta are the coefficients on the x's. The gamma is the state dependence parameter, the coefficient on the lagged outcome. But it turns out that because these parameters enter f, and f is nonlinear, these parameters don't really have a clear meaning. So we cannot sort of interpret them very sort of neatly. On the other hand, there are functionals of f, the marginal effects, which are easy to interpret, and typically in nonlinear models, when economists report effects, they really report these marginal effects. So for us, also in this paper, the main object of interest will be really the marginal effect. So for example, if you want to find the effect of change in employment status in a previous period, the effect of change in employment status in a previous period on the probability of being employed in the next period, it is basically this contrast. And this has an interpretation. So this has a meaning, and everybody is happy with it. And so we would really like to estimate this contrast. Now, of course, to estimate this contrast, you need the betas and you need the gammas, but we really need what we are really interested in this contrast. And similarly, you can come up with sort of other. So for us, we will be interested more in marginal effects. But of course, in order to estimate the marginal effects, we need to estimate the parameters. The marginal effect that we will be interested in estimating is the so-called average marginal effect. So you take this marginal effect and you average across all the individuals and across all the time. And this has a very nice interpretation. So, anyways, notice that this is a random variable that we want to estimate or predict. This is not an easy object to estimate because it depends upon these unobserved random variables. And we are not making any assumption about these random variables, these fixed effects. So one way to, and of course the marginal effect, the average marginal effect also depends on these common parameters theta. So in order to estimate these marginal effects, you first need to estimate the common parameters theta. And one natural, because it's a nonlinear model, the distributions are being assumed, one natural approach is do maximum likelihood. Unfortunately, maximum likelihood doesn't work. And this is a very classical problem. It is sort of well known since the mid 40s, 1940s. So let me just quickly say this because I just want to show you some results. Here's the likelihood for the model. So this is just to give you an idea of what goes wrong with the maximum likelihood, what goes wrong with maximum likelihood in these types of models. So we will write a likelihood for the common parameters, and we will treat these fixed effects as also nuisance parameters to be estimated. So if there are n individuals, you basically have n nuisance parameters. So you can already see the problem that as the number of individuals increases, the dimension of the nuisance parameter space increases. And basically, not surprisingly, a standard maximum likelihood, which requires sort of a nice compact parameter space, sort of the standard assumption gets destroyed right away. And so it can be shown that when you compute the maximum likelihood estimator, theta tilde, in these dynamic models, it can be shown, also in static models, but I'm just giving you the result for the dynamic models here, that if you let n go to infinity and t is fixed, then the MLE is simply not consistent. The p-lim will simply not be theta naught. On the other hand, if you let both n and t go to infinity, the MLE will be consistent. But if you now try and compute its asymptotic distribution, the limiting distribution is asymptotically biased. So you can see that the mean of the distribution is not zero. It's incorrectly centered. It's like a non-parametric estimator where even though the rate of convergence is not slow, it is standard, the classical rate of convergence, the total sample, square root of the total sample size, n times t. Yet there is an asymptotic bias. And so a lot of effort has gone into sort of solving this incidental parameters problem. So this is called the incidental parameter. These lots of nuisance parameters, incidental parameter problem. And so there are several ways of you can Yeah, so there's several ways to do this. You can orthogonalize parameters. You can do bias correction. You can do bias correction explicitly, meaning come up with analytical expressions, or you can do the jackknife if the bias corrections are sort of too complicated. You can compute integrated likelihoods by coming up with sort of clever weight functions that remove the bias. So you don't do explicit bias correction. You do implicit bias correction, and you can compute another integrated likelihood, which is what we do by sort of first transforming the nuisance parameter. So it turns out, again, I don't have the time to explain all this, but the integrated likelihood that we propose in a paper that came out last year, year before last, sort of does quite well. Yeah, and so there's several ways of doing this, and this seems to work quite well. So, okay, I skipped the interesting stuff. So here's the marginal effects. Oops. How do you estimate the marginal effects? So it turns out, so this is the marginal effect that we want to estimate. You write it as just a sample average, so just write in compact notation as a sample average. And you can estimate the marginal effect by sort of this object, where the pi's are weights that have to be constructed carefully so that the bias gets removed. Remember, we are not making any distributional assumptions. And it turns out that this estimator works. Works in what sense? That basically, if you the p-lim of m hat, the estimator converges with or coincides with the p-lim of m. Both are random variables, right? So we are sort of predicting these random variables, and as n and t go to infinity, both the p-lims basically coincide. So. Okay, so here's an example just to show you how this works in a simple setting. I'm just going to show you some pictures because it's almost done, and I will only show you pictures for the marginal effects. So you can compute the marginal effects for different kinds of regressors. So X1 is a continuously distributed regressor. So I'm just reporting, I'm just showing you these pictures. The top row is a logit model. The bottom row is a probit model. The reds are MLE, and you can see that the MLE is shifted far to the right. It is not closed. It is not centered at zero. The MLE is behaving really. This is the MLE of the marginal effects. The bias corrected is blue, and our estimator, which we call the MILE, the maximum integrated likelihood estimator. The bias corrected works. Sometimes it works quite nicely, but typically the MILE, the one that we propose, seems to do better. So again, this is preliminary work. We have shown how to estimate both the common parameters and the marginal effects using an integrated likelihood framework. We are finishing so now we have to finish the theory for dynamic models. The method that we use, the main disadvantage, it works quite nice, but the main disadvantage is it's computationally very, very intensive. And all these simulations are done on the Uni Luxembourg HPC. Even then, it is computationally intensive. So we have to figure out how to reduce the cost. Thanks very much.